We have completed nitrogen and phosphorus, and you saw some of the vulnerabilities that India faces. Potash is another one which we will discuss today. So the lecture today will be all about potash fertilizer. We need nitrogen because of all the amino acids, protein, which all have nitrogen. And likewise, phosphorus is so vital because of all the genetic material which they have phosphorus. So these are, of course, very important, but so is potash. Potash is the third essential nutrient that you know. The reason why we require it is a bit different from, let's say, why we require nitrogen and phosphorus. It really improves the health of the plants. For example, the roots are stronger. It's a very good activating agent. It activates many of the enzyme systems, maintains turgor, aids in photosynthesis, reduces respiration, produces grain rich in starch. Okay. I mean, even though the thing may not, starch does not have potassium, but it facilitates that. Helps to build cellulose, helps retard crop disease. So it has a very important bearing on the health of plants. Just to show you what I mean by has a very important bearing, it's not as if you don't have any potash that things won't grow. Of course they will grow, but there will be a lot of difference. Like, for example, look at potatoes. Okay, you've got the nitrogen, you don't have the potassium here, and you're gradually increasing the potassium. And you can see that under the same conditions of growing, cultivating, the potatoes are much healthier and bigger when you incorporate potassium. Look at the oranges, makes a lot of difference. And in fact, Nagpur, which produces a lot of oranges, they are a large consumer of potash because of that. So much better quality of crops. Look at this. I mean, it also withstands insects. Many of these plants otherwise are vulnerable to pests, and those attack. I mean, not that only potassium will do it, but you can see without the potassium, minus K, and plus K with the potassium, you can see that this soybean, look at the plants look so much better. Look at maize. This is with potassium, without potassium, makes a huge difference. And that's why, you know, potassium is an essential plant nutrient. Actually, we did have quite a bit of potassium in our soils. So for a long time, people did not have to apply potassium. I mean, it was okay. But as we started making agriculture much more intensive, the soil started getting depleted in potassium. And especially after the Green Revolution, we've really tried to produce a lot more crop from the same agricultural area, okay, land. So the requirements have gone up. Now, we as such did not have any good source of potassium in our country. Just like phosphate also, you have seen we have virtually wiped out all our resources. But it's interesting that you know, way back in 1941, there was this paper, the potash industry in India, where these people actually tried to speculate on what could be some of the sources of potassium in our country. Most important in a way is that because, you know, we have got a long coastline and the sea has potassium. After you recover salt like sodium chloride and you get the mother liquor Bittern, it has something like about maybe around 2 to 3% of potassium. It's not too bad. So, one could integrate salt production with recovery of potash. Okay. And also we have some natural sources which I will describe to you. Then there are certain lakes and underground brines. Those also, they're like seawater in a way, maybe sometimes even more concentrated. So those were a reasonable source of potash. Then there is some saline earths which are present in some places where you can find small amounts of potassium. There is a very important mineral called feldspar, this one, which again has potassium. But these extracting the potash is not that trivial from these. Okay, but nonetheless, these sources exist. Animal sources. You recall that, for example, the trees used to be burnt, and that's how they got potassium carbonate. That's what led to the work on soda ash. But that is for the carbonate part. But the potassium is there, and then there are certain animal sources which I've tried to list out. And actually, in our country, and especially in Maharashtra, it's very important because this state produces a lot of sugarcane. Finally, you are recovering the sugar from sugarcane. I mean, that's what one is using, and we talk about molasses for ethanol. Neither of those contains any potassium. Ethanol doesn't have any potassium, nor does sugar. But if you analyze the sugarcane juice, there's quite a bit of potassium in it. So it's something quite interesting to look at, trying to recover the potassium from these kinds of sources. So this is very visionary. 1941, this was done. Mata Prasad was in the Institute of Science in Bombay, now Mumbai, and a very visionary person. He was also the first director of the Salt Research Institute, where later on I was the director. Extremely visionary, the way they kind of listed these things out. But let me tell you what it is, that there are some countries which are really blessed with good source of potassium. And one of those countries is Germany. Then there are other countries like Canada, which is got very good potash resources, Russia. So there are, and we'll talk about a few more. In fact, this is probably, I would say, in a way, the best source of potassium. This was discovered by this person, Rudolf Carnall, and he's the one who identified the deposits in Germany. These are known as the Stassfurt deposit. What he found was that actually this particular ore that you get is essentially a double salt of potassium chloride and magnesium chloride with 6 molecules of water. So this is one very, very important deposit, and the reason why it attracted so much interest is because recovery of potassium chloride from this double salt was quite straightforward, and I'll show you, how it's done. Now the other was what they found in places like in Canada, in Saskatchewan, where it was not a double salt, but it was what is known as sylvinite. It's really a mixture of potassium chloride and sodium chloride, not pure potassium chloride. Usually quite high amounts of sodium chloride as well. But this again was not bad. It's possible to recover potassium chloride from this kind of deposit. So it's not surprising that these countries therefore became very dominant in the area of sources of potash, and they were some of the major suppliers of potash, and even today they are. But something else happened. these countries, these two countries, Israel and Jordan, they are blessed with the Dead Sea. The Dead Sea is a very, very interesting place. And what they found is that the seawater there is very rich in potassium. And it's not just a question of being rich in potassium. When you evaporated the seawater and obtained precipitates, those precipitates were just like this, like the carnallite. So it became quite easy for Israel and Jordan then to really produce potash in large amounts from the Dead Sea. And today, I think probably Israel and Jordan would be maybe the largest supplier of potash in the world. There's another element that they've become very famous for, that is bromine. And in this Dead Sea, there's also a lot of bromine. I'll see if I get time. After I finish with potash, I'll maybe talk to you about bromine recovery for 10 to 15 minutes on Monday. What you'll always realize is that the countries that really are able to succeed are those who, one is, of course, they've got good technology. That's one. But their resources are very conducive for recovery of what you are looking for. So that's exactly what is the case with all of these people. Let me show you why carnallite is so good for recovering potassium chloride. As I told you, it's a double salt, which you can see over here. Now, what happens is that if you were to look at the ternary phase diagram of basically water, magnesium chloride, and potassium chloride, because these are the three constituents which you have. So you can look at the ternary phase diagram. If you are in a place, this point over here, and if you were to look at the composition, you extrapolate it, put it on the axis, and then you'll find out how much potassium, how much magnesium, and how much water there is. So this is the point for carnallite. This is the point in the phase diagram. Now, if you now contact it with water, so you add some water, so what will happen is that the carnallite starts breaking up. So what it does is that it releases magnesium chloride. Now, magnesium chloride is highly soluble in water, as you know, and so the magnesium chloride dissolves in the water. So you're moving along this particular path from here to here, which means that you're adding water. That's effectively what it means. And so over here it's carnallite. As you put in water, what happens is that the magnesium chloride goes into the water, but the potassium chloride you get as a solid. Therefore, you recover potassium chloride. You just have to filter or centrifuge, and the solid will give you potassium chloride, which is why it's so attractive as a source of potassium. And then, of course, as you're putting more and more water, you're decomposing more of the carnallite, and then finally you hit this point. Now, if you hit this point, this is the point where all of your carnallite has basically got converted into potassium chloride. Not all, but most of it. That's what you'll try to do. You'll just contact it with the right amount of water so that you maximize the amount of potassium chloride which you recover. Beyond that, if you put water, what it does is, again, the potassium chloride will start redissolving in the water. So you don't want to do that. So obviously, it's very important, therefore, to locate the point D and just make sure that you are adding the right amount of water to decompose the carnallite to recover KCl. You don't want the magnesium there. So if the magnesium goes into the water, there's no problem. A small amount of potassium also goes, and I'll show you what happens. Now, this diagram which I've shown you is for a pure carnallite. I mean, if you isolate this and you were to do the experiment, then you will get this particular situation. But what happens is that even in the Dead Sea, in all of these places, there will always be sodium chloride, which will also come out along with your carnallite. That makes the recovery a bit more complex. In fact, the recoveries tend to go down, when you have sodium chloride. So that's just something to know, and that's why you cannot apply this in a straightforward way. You also need to know how much of sodium chloride there is, and there will be a modification of this diagram depending on what is the sodium chloride content. I can write this equation then. This is carnallite contacted with, let's say, a certain amount of water, X. Now, in this literature of, when you're recovering things like potassium chloride, what you'll find is they refer to KCl as K2Cl2. And this is from Van 't Hoff's days. He was the one who generated some of the very famous phase diagrams. I think that they tried to kind of have an parity between divalent ions and monovalent ions, and the way they did that is really by expressing it in this way. But obviously, I can write it equally as 2y KCl. If you look at this and you look at the values of Z and Y, now this one K2Cl2 is the how much of this you actually get as a solid. So this is solid, and this part is all in solution. So maybe I'll put that down. I'll put it as solid. And here, whatever is in bracket, I'll put it as liquid. Now, these are the optimum values for a system where it's absolutely pure carnallite. And you can see that the value of Y, for example, is 0.425. But this is K2. So this actually in terms of K becomes equal to 0.850. Because this is 1, then this is 0.85 K, which means that I can recover 85% of my carnallite as pure solid over here. So that's what it means. The rest of it goes into the solution along with all the magnesium chloride. Magnesium chloride doesn't come out of the solution, that remains. Only the potassium is left behind when you decompose, and so the solution has this composition. So if you were to do a mass balance, and you see this is 5.5 K2Cl2, so that will be, I can write it as 10.1 as K, and then Z has a value of 0.0138. So if I were to multiply 10.1 into 0.0138, that comes to 0.139. So your potassium is distributed now with roughly about 0.85 here, and the rest in the solution. So 85% is what you will recover. There will be a margin of some error. I might ask you some questions around these kinds of things and ask you to calculate how much is the recovery and things like that for different situations. As I told you, if you have sodium chloride in the system, then your recoveries are less, and typically you may recover something of the tune of 70 to 75% of your potassium chloride, not more than that when you're here. So those are some of the complexities. Graphically, you can see that, for example, say I'm taking a certain amount of water and I'm increasing the amount of carnallite which I'm putting into the water. What will happen is that initially everything will dissolve, and after some time what you will see is that this is potassium, this plot, that your potassium is starting to come down. So obviously it is the difference which I recover as the solid, whereas magnesium chloride concentration keeps going up in the solution. This comes down and this goes up. It's partly also because of the common ion effect that the potassium chloride gets thrown out from this solution. So this is really the kind of a profile that you will get. Is this clear to everyone?
So, what did you say for the Y becoming 0.8?
This one, I'm saying that Y over here, if you look at the value, it's 0.425, right?
Yes, sir.
Okay, but it is K2. So in
Yes,
terms of
yes.
K, it is 2 into 0.425, which is equal to 0.85.
Yes, sir.
Okay?
Yes, sir. Yes.
So, and this is 1. Okay, I'm starting with 1. And so I'm getting 0.85, which is 85% as solid. All right?
Yes, sir. So one more doubt, sir.
Yeah.
So all of this occurs at 20 degrees Celsius.
Yeah. The data that I am showing you would be data which is generated at 20 degrees centigrade. See, in a field, you can never have such a strict temperature control, but it would be under ambient conditions. If you are at something like 35 degree or 40 degree, which can happen in our in the summer months over here, what that tends to do is that the losses of potassium tend to be a bit higher, because all the solubilities go up in water. Okay.
Yes, sir.
Now let me show you another very interesting thing. I told you about the Dead Sea, and that Israel and Jordan are really they've captured the market, with selling potash. You will also be able to understand the nuances of technology, the nuances of composition. Like if you say, hey, look at potassium, you've got quite a bit of potassium in sea bittern. What's the problem? In fact, you've got maybe even more than in the Dead Sea. So what's your problem? Why can't you recover? If you don't know the phase diagram, then you will make such comments. Okay, but if you know how subtle some of these things are, then you'll realize what a difference it makes. Okay, now tell me one thing. So if you look at this, which I'm showing you here, is the composition of sea bittern. Sea bittern means it is, as I told, as you know, the bittern is really after salt is separated out from seawater and it all gets very concentrated, then what you have left is very bitter in taste, and from that we call it bittern. And we have this place in India, which is, we are actually blessed. Okay, this place is the Greater Rann of Kutch, this area. And what you have is, there is a creek over here, it's known as the Kori Creek. The seawater gushes in through the Kori Creek into the Greater Rann of Kutch. And this Greater Rann of Kutch has like a shallow basin type of a topography. So once things get in, they cannot come out. I mean, they're just stuck there. Okay? So and because this is a very arid region, so it keeps on evaporating the seawater, and all the salt starts crystallizing out. You can see this satellite image. How it's all white. Okay? This white is all salt. Okay? But within that salt, obviously the mother liquor doesn't disappear. It's there. So there is profuse amounts of this sea bittern in this particular place. This actually is one of our very valuable assets. In fact, some of our very big bromine recovery plants are here because the bittern also gets very concentrated in bromide. So it's easy to recover bromine. And nobody was actually recovering potassium from here. But my colleagues they had actually recognized the importance of this place. And in fact, they are the ones who did the survey for ground truthing of the satellite image, which was generated by ISRO. ISRO and our institute, they had actually generated this data, maybe in the mid 90s or late 90s. So very interesting. Now, if you see the Bittern and the Dead Sea brine, sodium you can see quite comparable. Potassium, if anything, it's a bit higher in the Greater Rann of Kutch, this Bittern. Magnesium, okay, not too bad. Chloride, comparable. What is different is sulfate. And you remember when we were talking about salt quality, etc. Now it so happens that seawater, because it has a high level of sulfate, and because the sulfate is much higher mole-wise compared to calcium, so even when you evaporate, only a part of the sulfate is removed as calcium sulfate, and the rest of it remains. And that is keeping on getting concentrated because magnesium sulfate is also highly soluble, so is sodium sulfate. So there's no reason for these things to really come out. It's only the calcium sulfate which is low, and that's why, to the extent that you have calcium, the sulfate goes down. Rest of it remains. Whereas in the Dead Sea, there is no sulfate. No, it's virtually zero. So this is the reason why when they evaporate, they end up with carnallite, which is KCl MgCl2, because MgCl2 is very high, and I've got KCl. So it evaporates, and now this is another thing that you must remember, that double salts have a property quite different many times from the individual salt constituents. So for example, whereas potassium chloride and magnesium chloride independently have quite high solubilities, magnesium chloride of course is much more, but still their solubilities are not bad. But in the presence of each other, when they form carnallite, the solubility goes down drastically. And so what happens is that when you evaporate, what you'll get is neither potassium chloride nor magnesium chloride. You'll get the double salt, which is KCl MgCl2. What happens in our case, which is all based on seawater? This, by the way, is the phase diagram which we owe to Van 't Hoff. Van 't Hoff was the one who actually prepared this phase diagram. It's very, very complicated, and these are all different kinds of double salts and more complex salts in some cases. We have gone from potassium, magnesium, and water now, because there's the element of sulfate and chloride. You can show this in 4 axes like this. I don't want to go into the details of how these phase diagrams are actually developed, but those of you who are interested may want to read up more. But what is very interesting to note is that this region is basically carnallite. You can see this is carnallite. This carnallite region is the one where I have got fairly high amounts of K2Cl2 and MgCl2. So over here, I will end up forming carnallite. What happens with seawater if I keep, or sea bittern, and if I keep evaporating more and more? You do not get this, because now what's happening is that we are actually shifting away from magnesium chloride more towards the magnesium sulfate. So this, what you get, this particular region, you get a double salt which is known as Kainite, KCl MgSO4. That's all. That one was KCl MgCl2, and this is KCl MgSO4. Nothing else. But that is the difference between somebody minting money, because carnallite is very easy to decompose and to recover KCl from, as I showed you. Not true for Kainite. Kainite, if you contacted water, it doesn't give you KCl. What it does is that it transforms itself into another double salt, which is K2SO4 MgSO4. This one. This is what you get. And it's not a trivial job to try and recover potassium from here. So even though you saw that paper 1941, they've talked about seawater as a source, and lot of work has taken place since the 50s in trying to recover potassium, but people got stuck. So you'll keep saying sea is very rich in potassium, but you're not able to do anything about it. Okay? So that was the issue.
So the sulfate is higher, right? So like we did in the case of salt, why
Yeah.
can't we add additional seawater in stoichiometric
Not
ratio?
seawater. There we added calcium chloride. You remember?
Yes, sorry, calcium chloride and then get the gypsum
Right.
out.
But then you have to look at the vastness of the area, and there's no calcium chloride available. So you'll have to move the calcium chloride from somewhere. You understood? In fact, it's a very good question you have asked. Brilliant. Because that's exactly what we did, but not in the Greater Rann of Kutch, but in the Little Rann of Kutch. Because in the Little Rann of Kutch, there was a soda ash plant of a company called DCW. They were chucking it, and it was creating a mess in the Little Rann of Kutch. A lot of the wild asses and all were dying because of that discharge. And so one could use that and do exactly what you're saying. But in the Greater Rann of Kutch, there is no source of calcium chloride. You can do something, which is that you can take limestone, which is available in the vicinity, and react it with acid. But then again, you'll require acid to be brought in. Those all add to the cost. That's what made it a bit complicated. Now, the question that you have asked, that is exactly the technology that has been developed, but in a slightly different way. And I'll come to that. So, and the plant has come up. There is a plant which is now producing over 1 lakh tons of potash in the Greater Rann of Kutch. The technology is a bit different, but ultimately the sum and substance is not very different from what you are saying. It's a very good question, but we will come to that a bit later. Is that all right?
Yes, sir.
And this is the Dead Sea. You can see these are massive pipes. Look at the pipeline, which is bringing in the seawater from the Dead Sea, and then those go into the salt pans, and further evaporation, etc., takes place. And I thought let me put the phase diagram of this again here. People are quite ingenious. They were always grappling with this problem of sulfate in the seawater, and is there a way to solve it? Okay. And it's actually based on some work which was done much earlier, I would say in the 20s, I think, by a very famous scientist called Joel Hildebrand in Berkeley. Hildebrand was actually working on phase diagrams and salts. And what these people had suggested, and it was based on some brilliant observations, that if you take sea bittern and you heat it up to something like 100, because this bittern, its boiling point is very high. So you can even heat it to about 110, 120 degree centigrade. The water doesn't boil over. Water activity is so low. If you heat it, what happens is that the magnesium is there, sulfate is there. It forms magnesium sulfate, which is anhydrous, just MgSO4, not with any molecules of water. And the magnesium sulfate drops out of the solution. What a remarkable thing. And then I can separate out that magnesium sulfate. It's great because you can make magnesium sulfate itself is very important as a chemical. And once you've then taken the filtrate, now the filtrate does not have any sulfate. and so you can now evaporate the filtrate, and you'll get carnallite. Is brilliant stuff. So, in fact, my former colleagues, I mean, I haven't met these people, but they actually worked on this in the 60s. Very brilliant chemical engineers, Dr. Datar, Dr. DJ Mehta, Dr. Sangvi, all of them were, these two were extremely fine chemical engineers, brilliant. He was probably one of the finest physical chemists, who actually learned how to interpret all phase diagrams. Brilliant person. Most of them are no more. Only this person, I believe, is still alive. But they're all not here. They're all left for their heavenly abode. Okay? So what they did was they were bold enough to try and set up such a plant. Okay? It was a semi-commercial plant, small plant, 3 tons per day, more like a pilot plant, where what they were doing was they were heating the bittern, as I told you, and then they were filtering, recovering the magnesium sulfate, and then they were putting that into the salt pans, the filtrate, and evaporating and getting carnallite, decomposing and doing it. That was great. In fact, at that time, we used to have a very reputed organization called the Industrial Consulting Bureau. It changed its name to something else later on. Very nice organization. So these people actually came, they validated the process. People who come from all over the world to see, this technology being practiced. But sadly, after about a year of operating, they had to abandon the whole thing. And there were 2 reasons for it. As one of my colleagues explained to me, who was familiar with what was done here, I've never seen this plant. One was, it was very energy intensive. Can you imagine heating up such huge volumes of bittern, which have only 2% of potassium chloride? Can you imagine how much volume of liquid has to be heated to about 110 degrees centigrade? So that was one. Second was, they could, when they did the separation of the magnesium sulfate, and then they were trying to get the filtrate, obviously these things have to pass through pipelines, etc. It was very difficult to keep it hot. It doesn't matter how good the insulation was. And now what happened was that it became super saturated in carnallite. So all the pipes, etc., got choked with the heavy crystallization of carnallite. I mean, you got the stuff, but you got it in the wrong place. You got it inside the pipes. So these were important. The third was where they had set it up, somewhere I think in near Kandla port. It was only linked to salt production. But salt production actually can give you only a limited amount of potash. So it was the wrong strategy in that sense. They should have gone to the Greater Rann of Kutch, which they didn't do. Maybe because they were not aware of it at that time. So the raw material supply also was not so hot. I mean, it was okay for a 3 TPD plant, but to, let's say, put up a 10,000 ton plant was a difficult proposition. Now, what you said, that it so happened that there were some places in the Little Rann of Kutch where there was sulfate, but the sulfate levels were low. So there was some kind of a manipulation of composition, etc., which was tried around 83, 84, but nothing really came out of it, nothing to really feel happy about. And so it was very sad that from 41, people started working, decades passed, and India was not producing 1 gram of potash.
So, if this same plant, sir, was at the Rann of Kutch, sir,
Yeah.
all these 3 problems could have been solved, sir.
No, your biggest problem, actually not a problem really, you can solve it, would have been that to heat up the bittern. Actually, you might be able to use solar energy,
Yes,
to
sir.
heat it up to that temperature.
Yes, sir.
In those days, that technology did not exist. Later on, in fact, maybe partly for this reason and for other reasons, the solar pond was worked on, where you could actually reach temperatures of 100 degree. And in fact, the beauty is that if you reach that temperature, the magnesium sulfate would drop up in the pan itself. I'll just decant off the rest, from there. It actually, that's a brilliant suggestion. Let me put it, maybe all the problems would have been solved if it was done in GRK. Okay, that's what you're saying, isn't it?
Yes, sir.
So you got some hang of it. Now the point is that what were they trying to make? They were trying to make potassium chloride. That is what you get from carnallite. And why were they trying to make potassium chloride? Because everything that we were importing in our country was potassium chloride. It's known as muriate of potash. So everybody, muriate of potash, muriate of potash. So these people, their brains got hijacked by this constant focus. We must produce potassium chloride in our country. So everybody was trying to make potassium chloride. Now, I was very, very lucky that around 2001, the Ministry of Fertilizer had invited me, and they wanted to take a stock of what is going on in our country in potash. Is there any hope that we'll get potash? Because there was such a drain on foreign exchange reserve. Our subsidy bill had skyrocketed. So people said, look, we've got to do something. And then, I was telling those people about all the valiant effort that was made by my former colleagues and how they had actually made a plant where you could make potassium chloride. One of the people who was listening in was this man, Dr. J.S. Samra. He was the Deputy Director General of the ICAR. He wrote me he actually told me this while I was there itself in the meeting. He said, Dr. Kutch, why is everybody trying to make potassium chloride? You are saying that the sea has a lot of sulfate. And I said, yes, it's got a lot of sulfate, but the phase diagram is a problem and this, that. And he said, yes, but sulfate is a very important nutrient for plants. It's the fourth essential nutrient. Today it is NPKS. So he said, seawater has sulfate. You are trying to recover potash. So why don't you see if you can recover potassium sulfate instead of potassium chloride? And I told him that, look, I mean, it's not as if people have not worked on that. And I said that we will look at it. And he was so keen on it. He sent me this letter. What he said is, you have mentioned that residue bittern after salt recovery contain carnallite, which is a rich source for the production of MOP and SOP. This is wrong. Okay. From the crop production point of view, sulphate of potash is much desirable than muriate of potash. Sulfur contained in SOP is also one of the essential elements for the plant growth. And then he said, look, SOP is actually a costlier fertilizer than MOP. So why don't you try to make SOP, sulphate of potash, potassium sulfate rather than potassium chloride? And he also mentioned that it is especially good for oilseed crops, because we produce a lot of oil seeds. We have a huge requirement for oil. So that was his focus. And that got me thinking that are we just doing the wrong thing? And is that the reason why we got stuck? Because we were just trying to be a copycat of the Dead Sea. This is a letter which I treasure. All of us need to be put in the right path. Never be a copycat, Don't try to make our normal sea into the Dead Sea. It's futile. So let me tell you, potassium sulfate, of course, is very, very important. It's not as if Samra is the first person to suggest potassium sulfate. It is made by what is known as the Mannheim process. This is identical to our Leblanc process. You remember when we converted sodium chloride into sodium sulfate? What did we do? We took sodium chloride, reacted with sulfuric acid, formed bisulfate, which was an exothermic reaction, and then the next step was endothermic, and you heat it up with more sodium chloride and you get sodium sulfate. Identical for this. This is known as the Mannheim process. Who developed it? Not surprisingly, the Germans, because the Germans are the ones who had the source of potassium chloride. The Germans realized that potassium sulfate is a better fertilizer than potassium chloride. There's another reason which Samra has not mentioned about. You see, the chloride is not only not required by the plant, but is harmful to the plant. It's harmful to the soil because all it does is that it raises the osmotic pressure. There is a salinity index which is caused by the chloride. So potassium sulfate would be a much better fertilizer, no question about it. And so this is the way they are making it. Roughly about 60% of all the potassium sulfate in the world is made by the Mannheim process. The problem is that you get HCl as a byproduct. The question is, what do you do with all this HCl? You can say do this, do that, but it's really not so easy to consume these vast amounts of HCl that are formed. And so this is one of the primary problems. But arising out of this, about 3 years back, one of the final year people had done a home paper where this kind of an idea was integrated with something else, where in fact we ended up actually using large amounts of HCl and finding a way to make good use of it. Maybe I'll tell you about that. Now, so that is one way, the Mannheim process. But there is another process which is known. You let the seawater evaporate and you'll get Kainite, as I showed you, which is KCl MgSO4, roughly about 3H2O. Now, if you contact this with water, I told you that it ends up forming shonite, K2SO4, MgSO4, 6H2O. You get this. What is very interesting is that you can take this and you can react it with potassium chloride. All these are ambient temperature processes, and you can get potassium sulfate as a solid, and you'll get magnesium chloride in solution. So there is a way of making potassium sulfate, but let me tell you what are the problems with it. One problem is that you never get pure Kainite. It's always contaminated with a large amount of sodium chloride. So you have to remove that sodium chloride. The way the sodium chloride was removed is there is a technique of froth flotation where you put in some surfactants. These are typically the surfactants that are used. And what it does is that the surfactant attaches itself to the Kainite, and it also picks up a lot of air. So it becomes like a froth and it becomes very buoyant. The sodium chloride sits at the bottom. So you can then lift out the Kainite, and because you're contacting it with water, you don't get Kainite, it forms shonite. So you'll end up getting a shonite which is quite pure and almost free from sodium chloride. So that's a very nice method, except these plants of froth flotation are very tedious to operate. It's not a great technology, but there was a way of solving it. That was one. The other problem is, which was a huge environmental problem, that once I've done this, there will always be some amount of this surfactant which will be go out with some effluent streams, and nobody wanted that, because if these things go into the soil and water, it can create havoc. So people were always very scared of using any of these organic these surfactants and doing flotation. So that was something that people were wary of. They didn't want to do it. But you can see that after the floating, the sodium is become zero. There's no sodium. That way, it's a wonderful technology to separate out sodium chloride. The other problem was that I had to again react it with potassium chloride. The question was then that, but we don't have potassium chloride, so how will I make this? But if they had been a bit smart, they could have actually imported potassium chloride. So they could have used imported potassium chloride, reacted it with the schonite, which they would have got from our sea bittern, and that way, roughly about half of the requirement of import could have been reduced. That would have been quite a smart thing to do. But then this was coming in the way, the froth flotation. The other is, just like I showed you that how magnesium sulfate can be taken out, if you take schonite and heat it up to a high temperature, you can actually leave these things in solution, and only the potassium sulfate you will recover as a solid. But again, the problem of heating to a high temperature and doing all this, so this process never became popular. It was more this process that was of interest. But because of these constraints, this also never really took off. I wouldn't say that it was a complete failure. It was actually practiced. They put up a plant. By the way, this is the froth flotation unit. There was a plant which was set up in Tuticorin. There was another plant set up in Burma, in Myanmar. And so the technology was demonstrated, and it was actually being used for the manufacture of potassium sulfate. Many times they did not manufacture potassium sulfate because of the problems that I told you of finding potassium chloride. But they found that the schonite is itself a good fertilizer. You can actually add it to the feed. And so that is what was being done. But it was not a very attractive technology. And also because people did not get too much of money for the schonite, because the potassium content was quite low in schonite. And so finally, this also faltered, and the technology didn't really take off. Let me tell you about our technology, which was developed around maybe around 2004-5 or thereabout. This is what is now being practiced in the Greater Rann of Kutch. And in fact, I just dug out this advertisement, and they were first assembling the team which was going to carry out this in the Greater Rann of Kutch. And so what they did was, this company, they licensed the basic technology from us. I'll tell you what the technology was. But because we didn't really have the wherewithal to do detailed engineering, and they were going to set up a 100,000 ton plant. So they basically went to another company called KU Tech in Germany, and those people, they also modified our process to some extent. And then that's really the process that was set up. So this was set up, I think, around 2012 or 13 or something, 14, maybe around that time. Took a long time. So this is the plant where the sulphate of potash is being made in the Greater Rann of Kutch. They acquired 60,000 acre of land, because you have to evaporate the seawater, and only after you get Kainite does the process begin. And I'll describe to you the process. And you can see the vastness of this place. And so this is all the salt. So they were actually also selling about 3 million tons of salt. A lot of the bittern they were collecting. This is the bittern. And today, they market this sulphate of potash over there, which is produced in the Greater Rann of Kutch. So let me tell you what is the process, and it's actually a fairly simple process, and it actually draws on the question that was asked about desulfitation, calcium chloride, but done in a different way. So let me explain to you the process. Maybe I'll send across the patent, which was granted in 2006, the US patent. So what you do is, first you evaporate the seawater, and so you can imagine that you require a lot of land for that. That's the first thing. So that's a limitation of the process. So you get kainite, this stuff, then it is decomposed with water. It's all done on ambient conditions. There's no heating involved. Ambient temperature, ambient pressure. And centrifuge, and you get your schonite. And we saw that schonite can be reacted with potassium chloride to form potassium sulfate, sulphate of potash. So let me tell you where this potassium chloride came from. Now, when you centrifuge this after decomposition and form schonite, this liquor itself has a lot of potassium in it. It has potassium, magnesium, sulfate, a lot of sulfate, which was there. All of it ends up, here. Part of the sulfate goes into the schonite, and the rest of it ends up here. Okay. So now it was done in a way. Now I hope you'll understand. Although I've written KCl NgSO4 3H2O, you can imagine that there is quite a bit of sodium chloride. As I told you, because sodium chloride also separates out when you're evaporating the stuff and getting kainite. So enough water was added to dissolve out all the sodium chloride. So the sodium chloride solubility was established under these conditions, and the water amount was determined based on the amount of sodium chloride which had to be dissolved. So it dispensed with the need for froth flotation. Okay, that was first. But obviously there were more losses, like quite a bit of the potassium chloride, this kainite, ended up in the liquor, in the mother liquor. It's not as if all the kainite get converted into schonite. But I said, no problem. We finally require schonite, and we also require potassium chloride, and then found a way of trying to recover potassium chloride from this liquor. How was that done? It has sulfate. So potassium chloride means we need to get carnallite. So what we then did was, because there is so much of magnesium all around, the magnesium chloride was reacted with lime after slaking, and it formed magnesium hydroxide. Now, magnesium hydroxide is itself a very important material. MgO, magnesia, is one of the best refractory materials. So we realized that there is a good opportunity to find value from magnesium hydroxide. And what will I get? I'll get calcium chloride. That calcium chloride was then used to react with this schonite and liquor, and it separated out gypsum. Now the liquor that you got is free of sulfate. So you can actually evaporate, and you'll end up getting potassium chloride. But that potassium chloride is not pure potassium chloride. That is the crude KCl, NaCl, and that is refined to separate out sodium chloride. You take advantage of the fact that sodium chloride solubility is independent of temperature, whereas potassium chloride solubility depends on temperature. I'm not going into the details of this process. Subsequently, of course, another process was developed based on wet sieving. What was found is that the potassium chloride crystals are much smaller than the sodium chloride crystals. So you could actually sieve out the sodium chloride. So that drastically reduced the cost of separation. And so you end up with a potassium chloride solution, which you react with your schonite, and you end up with potassium sulfate. So potassium sulfate is the product that you're looking for. And here, both the potassium chloride and the schonite are really coming from your kainite, but coming in this way. This is a process which became quite attractive, and also because all this operation is all room temperature operation. You need heating really only at this point, and your input is really the kainite that you get from the field, and you need lime. So you have the input is lime, and the lime of course gets converted into gypsum which is a saleable product. So that is really the technology that was developed. It conforms to the specifications of sulphate of potash. In fact, is marginally superior than whatever is the specification. So there's absolutely no problem in selling this product. So this is how sulphate of potash was made in our country. I think that these people were trying to expand it to about 3 lakh tons of production. This was also licensed to Tata Chemicals. I don't think Tata Chemicals has yet gone into production, but they acquired the technology. Probably at some point they will invest and set up a plant. The problem is, you see that India requires something like 5 million tons of potash. What you saw is a plant which is producing 100,000 ton, and even if we increase it to 300,000 tons, 0.3 million, that's not even 10% of our total requirement. Now, one of the constraints of that is really that the area that you will require for evaporation, because if you have to produce, let's say, 5 million tons, firstly you have to make sure that so much of bittern is available, assuming that it is, but that much of land which you'll require, maybe it's not available. That got us thinking. The second was that one of the important requirements in any of these technologies is that you have to have plenty of sunshine to do evaporation. And there's always a threat that suppose I recover my kainite, and where will I keep it? I have to make huge mounds of this kainite. And suppose there is some unseasonal rain and everything dissolves, then your effort is all gone. So there's always this vulnerability to climate. And in fact, the rains in the Greater Rann of Kutch have been higher, in the last 20 years or 15 years at least, than it was in the past. So there's always that vulnerability. And the third, I'd already, I think at some point shown this sketch, that to recover kainite, your relative humidity cannot be higher than 60%. This is the onset point. Where you are actually stopping kainite production, your relative humidity has got to be less than 40%, which means that you need very arid areas. And if there is a lot of humidity in the atmosphere, then there's a problem. I mean, the Greater Rann of Kutch, of course, is an advantageous location for that reason, because it's more arid. But still, you can have a problem, that you're not able to evaporate it. So, when you know that there is this kind of a problem, what can you possibly do? Can you think of anything else?
Excuse me, sir. Please could you repeat your question?
Yeah, I'm saying, you see, all of this is based on what? It's based on fractional crystallization through solar evaporation. I'm taking the sea bittern, it's getting evaporated by sunshine, and at some point, the kainite is coming out with some sodium chloride. All the rest, the magnesium, the rest of the magnesium, etc., remains in the mother liquor. And so I've got my raw material, which is kainite. But I told you that there is a vulnerability in terms of the weather, unseasonal rain, all of these things which can create a problem. So I'm asking you, can you think of any, you don't have to know the solution. I just want you to say what you might think of as a possible solution to this kind of a problem. Is there any other better way to recover potash which avoids these weather effects?
Transporting it to another place.
Oh my God, you can imagine the transportation cost.
So nearby only, as in what we are considering is an open place that is prone to weather conditions.
Yeah.
If we make factories nearby or storage facilities nearby.
Good point. You are saying stored the kainite in closed area, right? That's what you're saying.
Yes, sir. Yes.
Okay. Good. Anything else? Which is a more fundamental solution?
So we could try not to keep surplus around.
Surplus. Oh, so you are saying just make sure that you are producing and using, right?
Yes.
Brilliant. Produce and use. I think that's a very smart idea. Only thing is evaporation and all that obviously takes place in a more favored way during a few months, whereas your plant is operating maybe round the year, and so balancing it out is not so easy because then you'll have to create a very large plant. You understood?
Yes,
Sir, in some way, if we can increase the rate of evaporation
Yes,
or
yes.
separation.
Increase rate of evaporation. Yeah, this is also a very good idea. Actually, you can add dyes, for example, a dye into the bittern and make it colored, and it will evaporate faster because it will absorb more of the light. There will be less reflection, e.g. by adding dye. Good idea. All of the ideas are good. Anything else?
So can we just store it underground in a hole or something?
Brilliant idea again. Store underground.
I use filters that separate ions.
Oh, you're getting there.
Ion exchange resins, we can use that to separate ions, and then that
Ion
would.
exchange resins to separate. So you are separate selectively, right?
Yes, sir.
That's what you're saying. In a way, what you're saying is not miles away from something else which was proposed. So let me take you through it. The question is that is it necessary that potassium can only be recovered by evaporating, then getting this double salt, then taking it forward? Is there any other way? What I would call as a dream. Don't forget about whether you can achieve it or not. A dream way of taking out the potassium.
Selective
Complex
precipitation.
formation.
Yes, you got it. I knew that someone will come up with the answer. Okay, great. This was something one was grappling with, that can something be done to precipitate out potassium? Again, let me tell you, it's not as if research had not been done. Some research was always going on in that area, but nobody really had come up with a solution which was actually implementable. In fact, this patent was granted in 2017, the US patent, on such an approach. And it's an approach based on knowledge which existed in 1925. Okay? I mean, the knowledge was not new. Okay? And what was that knowledge? What happened was, in those early days, when people used to estimate for sodium and potassium, about flame photometry. That's one way of estimating. But this person, what he found is that when you have got this bittern, and if you add into it bitartrate, anion, the half acid of tartaric acid, what he found is that it precipitates out potassium bitartrate. That was nice. Where did he get his clue from? This Muriate. I think he got it from something which everybody knows, but never put to use perhaps. If you are fermenting grapes into wine and it becomes ethanol, there is some amount of tartaric acid which actually gets generated as a byproduct, you can say, of this process of fermenting of grapes into alcohol and to make wine. Yeah? And people had noticed that on the underside of the cork, like you fill up these things and you put it into your wine bottles and leave it to ferment for maybe 10 years or 5 years or whatever. And on the underside of the cork, they always found a white precipitate. When it was analyzed, it was found that it is potassium bitartrate. So potassium bitartrate has a low solubility. It's something like in the Solvay process, it would never have been successful but for the fact that sodium bicarbonate has low solubility. And so that probably was the clue which this man derived, and he then came up with a new analytical method which was not dependent on flame photometry. And now, what happened was that we started thinking that does an analytical method only have to remain as an analytical method? Can an analytical method become a production method? That was the question. Why not? So one of the first things to do was that one took bitartrate and put it into different ions, which are cations, which are normally present in bittern. What are the ions? Cations are sodium ion, potassium ion, magnesium ion, calcium ion. These are the ions. What one found is that these ions, there's some precipitation, but it's all dominated by calcium. If you've got calcium, forget it. All the tartrate will be consumed by the calcium and you'll end up getting calcium tartrate. And that was true whether you were in a low pH range or in a high pH range. Even at 6.5, that was true. There was virtually none of this, But, one did another experiment where the calcium was left out from the study. Now, when the calcium was left out, something very interesting happened. The potassium, you can see very selectively precipitates out. Whereas, if the pH is higher, 6.5, 7, it is the magnesium which precipitates out. But here it is the potassium. So it was very interesting. Sodium doesn't come out in either case. Over here the potassium comes out, here the magnesium comes out. Then the question was that what happens to bittern as you are evaporating? We know that it comes out as gypsum, of course, but not only that, as you are evaporating more and more and you are forming bittern, what you find is because the limiting concentration is of calcium, so all of the calcium will come out by the time you have completely recovered all the sodium chloride. So look at this. This is calcium and this is potassium. Initially, when you are starting with, let's say, seawater, both potassium and calcium have almost similar concentrations. But as you are evaporating, your potassium concentration is building up and your calcium concentration, beyond a point when the gypsum starts coming out, of course it precipitates out, and by the time you have reached about the place where you recover almost fully the sodium chloride, it goes to negligible concentration. And mind you, this is a logarithmic plot. And these concentrations of magnesium and sodium, they all more or less increase. Sodium, of course, doesn't, because sodium, of course, will increase up to a point, and then when you recover sodium chloride, there will be an alteration in the concentrations. So what happened was, then we, from Tata Chemicals, we asked them that give us your bittern, because Tata Chemicals makes about 1 million tons of salt. So they gave their bittern, and then we evaporated it to the point close to where the carnallite will start coming out, the onset, the initiation point of carnallite. And this is the analysis that they provided us. Now what you see is there's no calcium below detection limit. So we have to now only worry about this. We don't care about this. And so what you do is you estimate the amount of potassium which is present in your bittern. You add bitartrate slightly less than the amount of potassium, because you don't want to lose tartrate. So let a little bit of loss take place of potassium, no problem, but tartrate loss should be minimized. So what happened was this equilibrium then took place. In other words, I take magnesium tartrate, and I'll tell you why we take magnesium tartrate. Magnesium tartrate, this is put into your bittern. The pH is controlled so that it is in a bitartrate form, which is around the pH of 3.5. So you adjust the pH, and promptly the potassium bitartrate precipitates out. Magnesium goes into solution, and you take out your potassium bitartrate. Now the potassium bitartrate needs to be converted into a more usable form, like potassium chloride, potassium sulfate, or potassium nitrate, things like that. So now what you do is that you can react this potassium bitartrate with effectively a magnesium salt. Don't worry about how it's generated, and the pH is lifted up. So now what happens is the magnesium comes out as magnesium tartrate, and the potassium goes into solution. And so suppose I've used something like, let's say, magnesium carbonate plus nitric acid. So I'll basically end up forming magnesium tartrate, this tartrate, and this bitartrate. Magnesium tartrate and the potassium will go into solution, and effectively you will be left in solution with potassium nitrate solution. And you can recover the potassium nitrate from that by doing a cold crystallization or something, and you get absolutely pure potassium nitrate. And you end up with magnesium tartrate. So now you take that magnesium tartrate, put it into the next lot of bittern, and you just continue with the process. Now, what was also found is that some amount of tartrate always tends to get lost in the bittern, which one could not afford to do, because tartaric acid is quite an expensive material, and that would have made the difference between making it successful and unsuccessful. So what happened was, you now that residual amount of tartrate which is there in the bittern, add calcium to it, because we know that it's got a very strong binding energy. So now that you can recover calcium tartrate, the residual traces of tartaric acid which we might have lost in the bittern, and calcium tartrate can, in turn, you can cook it up with sulphuric acid, and what will happen is you will get back your tartrate and you will get gypsum. So this is a very well-known reaction. So effectively, you're playing tic-tac-toe, and you're recovering the potassium as a precipitate. Subsequently, you're purifying it, whatever you're doing. So that's really the process that was adopted. The tragedy is that it has still not been applied to fertilizer manufacture. The first plants to come up were those who were making, all these firecrackers, and where they need a lot of pure potassium nitrate. And so those are the plants which came up in Tamil Nadu based on this precipitation process. There are a few other things which I don't want to go into, but what is interesting is that there is a crossover point. There is a point at which the calcium sulfate solubility increases and the calcium tartrate solubility decreases. Calcium tartrate solubility is higher than that of gypsum at these temperatures. So what happens is that in this particular reaction, when I'm doing the reverse, I'm taking calcium tartrate and cooking it up with sulphuric acid, you have to raise the temperature. You raise the temperature so that the gypsum solubility is lower than the solubility of tartrate. So what comes out is your gypsum and tartrate remains in your solution. So that's where, it's also very, very important to understand fundamental aspects of properties of molecules, like just not solubility. Solubility under what conditions? Solubility in presence of what all of those have a profound bearing on the kind of technology that you have. Now, so let me tell you another place where this technology has been applied during the last 5 years. I told you that there is a lot of potassium in sugarcane, and that ends up in the sugarcane juice. When you are making sugar, the sugar does not have any potassium, so it all ends up in the molasses. Molasses has something about close to about 12% of potassium chloride, quite a high concentration. Then what do? You take the molasses and you ferment, you get ethanol, and then you recover the ethanol, which we'll be discussing later on when we talk about petrochemicals and biofuels. And what you're then left with after recovery of ethanol is known as spent wash. That is what it's called, spent wash. And all the potassium is there in the spent wash. The spent wash also has large amount of organics, because everything does not get fermented. There is a fermentable portion in your molasses which gets converted into ethanol. The non-fermentable portion just remains. So what is done then is that you can recover biogas from that spent wash. All these distilleries now are big producers of biogas, which they use as a source of energy. Once you have taken out the biogas, the potassium is still there. What we thought is that why do you have to only think about precipitating out from Bittern? It should be possible to precipitate out from any solution, provided there isn't any calcium. So you can treat things and get rid of the calcium. And then what you can do is that you can try your potassium, and you can see that from this biomethanated spent wash, means after removing the biogas, removing the methane, one could recover potassium nitrate. And not only that, from this horrible looking liquor, this biomethanated spent wash, to all the processes that were studied, okay, one ended up with a very nice, clean effluent. So this is big enough that this came to the notice of the Prime Minister, and he congratulated the Institute for this innovative zero waste potash technology. And look, everything was need based, because there was a problem of land. So it was a compulsion to try and invent a new technology. That new technology, as one of you then so correctly said, is precipitate out. I don't have to evaporate, I precipitate. Once you have precipitated, and then you say, what's so holy about Bittern? I'll apply it everywhere. Wherever you get a chance, you see a solution which has got potassium and which is going waste, say, let me recover the potassium. This is another where it is being applied. These are seaweeds. This is being grown. When you crush these seaweeds, you get a juice, the seaweed sap, which is again very rich in potassium. Okay? And you can actually precipitate out, recover the potassium from that liquid. So that's another area in which it is being applied. So I hope you have got an idea about potash recovery. I think I'll stop here. Any questions? Is it all clear?
Yes, sir.
Yes.
Okay.